Hey, you know what? You can make graphene with just a laser. No furnace, no clean room, no $1 million lab, just laser and some tape. I'll show you how in just about 10 minutes. Hey, I'm Onik from Material Science and Engineering from Shanghai Jiaotong University. So let's get into it. So, laser-induced graphene, LIG for short. Today, I will explain the mechanism, the key parameters, and why this method is getting so popular nowadays. Here is a typical picture of LIG formation. You can see a laser light is positioning on a substrate, and we are getting, laser-induced graphene on a substrate. So let's delve into this dimension a little bit more. So to make LIG, you just need two items. First, a laser, the same kind you used in a laser cutters or engravers. Second, a suitable substrate, a material that can turn into graphene when it hit by the laser. That's it. No furnace, no vacuum, no classroom. That's why actually people call it a desktop revolution. So what's the most common material for LIG formation? The most common substrate which we use for LIG formation is a polyimide film or Kapton tape roll, which is actually ambered colored in color and used in electronics and 3D printing. You can see the polymer structure. It contains carbon, oxygen, nitrogen, hydrogen. When you heat it with a laser, something special happens. Let me show you the mechanism. So I will describe the mechanism by 5 steps. So what is the step 1? Step 1, the laser will hit the polyamide surface. That's our step 1. And in step 2, the temperature rises rapidly over 400 degrees Celsius, sometimes over 1000 degrees Celsius at the laser spot. So what happens when temperature rises in this region rapidly? In step 3, the polymer breaks apart. This is called pyrolysis or carbonization. The, in this step, the non-carbon atoms, for example, oxygen, nitrogen, hydrogens, turn into gas and escape. So what is remaining here? The remaining carbon atoms are now free. In the fourth step, they rearrange into the most stable structure, which is the graphene hexagon lattice. So, in this step, in this fourth step, we are actually getting the graphene, which we are calling about laser-induced graphene. So, what actually happens? The laser moves, leaving behind a trail of black porous graphene. Laser in, graphene out. That's our LIG. So, why polyamide? Why polyamide is the most common substrate which is used in LIG? There are basically two reasons. One is high carbon content. Firstly, it has very high carbon content. More carbon means you will get more graphene. So high carbon content is the main reason of using polyamide as a LIG substrate. So different substrates, for example, different textile substrate, wood or cloth, even food, which can have high carbon content, can be turned into into LIG. The second reason will be the aromatic rings, a stable structure which is made of carbon. These act like a seed, helping carbon atoms reassemble into graphene. So that's the basically two reasons why polyamide is basically favorable in LIG formation. There are several important parameters which actually control the quality of graphene. The first parameter is laser power. You know, in the if when the laser power is too low, you can see the point A. So material doesn't get hot enough. So incomplete carbonization happens. So we get a little graphene, not a very good quality graphene. So when the laser power hits to the optimal power gives high quality and porous graphene. This heat is actually turns the aromatic rings and the carbon content into stable graphene. But the laser power, when it is too high, you burn like everything, so graphene turns into dust. So the sweet spot, which we are calling, the B spot, which is the optimal laser power, it is typically 10 to 20% power of carbon dioxide lasers. Every laser is different. Every laser has a different kind of sweet point. So you need to make sure what you need to understand what laser power should I need, do I need to get a good quality of graphene. The next parameter is scan speed. So what is scan speed? Actually, it's how fast the laser moves. When the laser speed is scan speed is so slow, laser dwells too long in a same region. So it overheats and burns the graphene. You can see the point A. So the graphene quality is like bad. But when it's optimal speed, then it's give best quality. But when the laser moves too fast around the surface, so there is no enough time to reach carbonization temperature. So weak, incomplete graphene we get. So typical optimal speeds is like 50 to 200 millimeter per second. So this it also important parameter which is needs to be considered for graphene formation by laser. The third parameter is defocus. Every laser has a focal point. When it's on the perfect focus point, then the energy is most concentrated on the subject, and there is a very small spot. But when it is defocused, that means the laser spot is slightly larger, so lower energy density we achieve from the laser. For LIG, defocusing can create more uniform graphene. So when the spot is larger, that means you set the laser in a defocused position, more even heating, more uniform heating we get on the substrate. So the graphene we create is more uniform, more stable. But if you do so much defocus, so the energy drops significantly. So there is no such much heat to turn the substrate into graphene. So you have to tune it that also. So every laser is different. For carbon dioxide laser has a different kind of defocus point, which gives the optimal quality of graphene. Here we can see some SEM images of graphene which is produced by laser. So what does LIG actually look like? We can see this from the pictures. There are microscopic images which is called SEM, scanning electronic microscope. Look at the pores. There are tiny holes in the graphene structure. So this kind of structure we're getting from LIG, it actually depending on different laser parameters. When you set different kinds of laser parameters, so you will get different kinds of porosity. This porosity actually helps. It gives a higher surface area of the graphene, and which is used in a different kind of application. For example, sensors, supercapacitor, electrocatalysis. So these ports actually not bad. They are actually good quality for graphene. So you need to make sure the laser parameters, scan speed, its defocus and power, what we are getting, what we want to get, that also determine what laser powers we will use, because different laser powers actually give different kinds of porous graphene sheet. So actually, why it is getting popular nowadays? Actually, there are 5 to 10 reasons. I just list 5 reasons here. So there is no furnace. If we talk about like CVD, we talk about CVD. So in CVD, we need kind of 1000 degrees Celsius temperature. Obviously, it varies, but LIG works on just your desk. That's why it's called the desktop revolution. So LIG formation is very faster. Actually, it writes graphene at centimeters per second. Also, it's patternable. You can produce graphene in any shape. For example, you can produce in circuit shape, electrodes, logos. So laser is like your pen, and also it's very low cost. Basic diode laser you can get under $500 or this kind of things. So you will need here just the desktop. So actually we're calling it desktop revolution. So the LIG we just get where can we use it? So we know graphene is used in sensors, supercapacitors, electrocatalysis, and EMI shielding and wearable, functional textiles or these kinds of things. So LIG is similarly used in different kinds of, can be used in different kinds of sensors, making supercapacitors for its high surface area and porosity. So that's basically like the graphene application, because it's also graphene. So there is no debate about that. So we already know the advantage of LIG, but actually there are some limitations. It works on only certain materials, which we have already discussed, like polyamide, because it gives us high carbon content and aromatic rings. And also the other subject, for example, we have mentioned like wood, cloth, even food has also a high carbon content. So these kind of materials can be used in LIG. All materials available beside you can't use that for sure. And it also gets low quality graphene, so the conductivity of the graphene which we are getting from LIG will not as good as CVD, because CVD is a more controlled environment, so CVD, the quality will be less for this LIG than CVD. And also a laser required, you can say it as an advantage or as a disadvantage, no problem with that. So what actually LIG is getting nowadays popular, and even it's getting popular because we can use different sustainable substrate, for example waste clothing or something, and turn into a very valuable thing. So this is actually getting popular. So we have discussed about the LIG formation, how it works, but the fun fact is LIG was first discovered by James Tour's group, research group at Rice University in 2014. They were actually trying to do something else and noticed the black residue left by the laser was, graphene. So actually sometimes the best discoveries are accidents. So they are not intended to make graphene, but somehow they found it. It's also relate to the discovery of graphene. So everything is happening in the graphene field. Actually the first incident is actually an accident. So now you know what is LIG, so you can go tell someone, or you can suggest the video to them if it's useful. The thing is, we just produce LIG, we know how it produced, we know what substrate actually we are using. So we are using a substrate, and we are getting some LIG. How can we know that it's like good? Is it applicable? Is it its conductivity is good or not, or can it be used in supercapacitor or sensors or not? So these two parameters that actually determines this LIG is good or not. So in the next video we will go to the very basic understanding on what Raman spectroscopy tells us, and what sheet resistance of LIG means. That's the most important criteria for LIG. So we will discuss in the next video. If you're interested, please watch the next video. Thank you everyone, and this is Onik. Bye bye.